Okay, so let's start today's session. So in the last week, you have learned about the chromatographic techniques and their classifications, and the high performance liquid chromatography was uh, explained in brief, and the cell permeation chromatography, the mechanism, the theory behind it, and the instrumentation in parts, and also the calibration curve which we get from the GPC. Technique, and then sample preparation. And we also learned about the gas chromatography, their principle, theory, instrumentation, and other detection systems which are used in the gas chromatography, which is a very important part. Uh, and the GCMS principle and their spectrum. So I'll be covering briefly these topics. Then we'll go to the DTA analysis, how it works, and then the reverse engineering and its importance, and the types of reverse engineering for in general for rubber products. So let's start with the chromatographic techniques. So let's start with the chromatographic technique. So it is a physical method of separation in which the components to be separated are distributed between two phases, one of which is stationary and that is called a stationary phase, while the other, the mobile phase, moves in a definite direction. Chromatography is a separation technique that uses the size, shape, chemical properties, or the charge of molecules in a sample to separate the sample into its constituent components. So once again, chromatography is divided into two phases. Like it has two components: mobile phase and the stationary phase. Then there are different types of chromatographic techniques. So to classify on the basis of the bed shape. So on the basis of the bed shape, it is classified as column chromatography or planar chromatography. In the column chromatography, we have a column in which we have a these phases. So this is the stationary phase. This column is actually filled with some of the uh, material which absorb the uh, elements which we flow in it. So that in that way, since this phase, that is the stationary phase, is is the bed actually, and then the material which we want to characterize flows to it. So that is the mobile phase. Then we have a planar chromatography. Then, on the basis of the physical state of the mobile phase, so first one is the gas chromatography. So here we uh, inject our sample in a gaseous form. So that is why we call it as gas chromatography. And then we have liquid chromatography. So here we use a liquid sample, and again the column is stationary. So and the sample is mobile. Then, on the basis of the mechanism of the separation, so on the basis of mechanism, we have ion exchange chromatography, size exclusion chromatography, and expanded bed adsorption chromatography. So in the so first one is starting with the again the bed shape. So we have column chromatography. In this, the station phase of the setup is placed inside a tube, and the mobile phase pass through it. Then we have a planar chromatography. So in this, the stationary phase of the apparatus usually has a planar shape, and the paper chromatography and thin layer chromatography are the examples of the planar chromatography. Then we have the in the on the physical state on the basis of the physical state of the mobile phase, we have gas chromatography in which, as I already told, that the mobile phase is gaseous substance, and so these are again classified as gas liquid chromatography or gas solid chromatography as well. Then we have liquid chromatography, which is having mobile phase in liquid substance. So the sample is basically liquid. Then these includes the high performance liquid chromatography HPLC and reversed phase liquid chromatography RPLC. Then in the ion exchange chromatography, we have the mechanism of ion exchange, which is differently charged components of the mixture are separated with the help of different ions. Then size exclusion. So depending upon the size, we have different filters, and depending upon the size of the particles, this since their diameter, hydrodynamic diameter and hydrodynamic volume will be different, so that is how the components will get separated. And then we have the expanded bed adsorption chromatography, which common this is a common use for biochemical separation process. So starting with the most important one, that is the high performance liquid chromatography. This is most extensively used. It is a very highly sophisticated instrument. So in this, the stationary phase is again in the column in which a granular material with very small porous particles is present in the column, that is the separation columns, and the mobile phase is the solvent. So here we use the mobile phase solvent. Solvent is used in the mobile phase. The individual component of the sample migrate through the column at different rates because they are retained at a varying degree of interaction with the stationary phase. So suppose then I pass the solvent in the column, and then we inject the our sample. So depending upon the migration rate to the from the column, because the different particles will interact with differently with the stationary phase, so that is why we get the migration rate. So firstly, suppose element A comes, then B comes, then C comes. So likewise, the detector detects it, and then it collects the waste solvent, and the data get displayed on the PC. So there are different types of high performance liquid chromatography as well. So if the normal phase is having, in the normal phase, the column packing is a polar, that is silica, and the mobile phase is non-polar. So it is used for water sensitive compounds, uh, that have geometric isomers and cis trans isomers and chiral compounds. Then in the reverse phase, the column packing is non-polar. Example C18, C18. Material, and the mobile phase is water plus any miscible solvent, for example methanol. So it is used in the ratio of 50-50 or 80-20 likewise, and it can be used for polar, non-polar, ionizable and ionic samples. Then we have ion exchange. So in the column packing contains ionic groups, and the mobile phase is buffer. It is used to separate ions and cations. So depending upon the ion exchange, so this is basis on the mechanism of ion exchange, the separation happens. Then size exclusion, as I already told you, since there is a difference in the hydrodynamic diameter of the molecules, so their motion will be different, and so that is how they will be separated. So the molecules diffuse into pores of a porous medium and are separated according to their relative size to the pore size. So larger molecules will elute first, and the smaller molecules will elute later. Then the next technique is the gel permeation chromatography (GPC). Permeation chromatography is a type of high performance liquid chromatography (HPLC). So in the GPC, that is or the size exclusion chromatography, molecules on the basis of their size and size exclusion or hydrodynamic volume, it is a radius of gyration of the analytes. So it is used to determine the molecular weight distribution of the polymers. So suppose we have different polymers here, and this is the largest and this is the smallest, depending upon their elution volume. So that is the retention time. So depending upon the time and also the molecular weight, this kind of curve will be formed, and the larger particles will lie in this region, and the smallest particle will lie in this region. So this is again size exclusion. So depending upon their size, the separation happens. So the molecular weight can affect the a polymer's brittleness, flow, and compression properties. The MW is related to the strength and properties and impact resistance. Mg is in relation to the elongation and flexibility from the gummy rubber. Uh, then Mg plus 1 is related to the die swell or extrusion parameters. This molecular weight determination method is not absolute, but it is used for polymer standard and with similar structures to correlate the elution time and molecular weight. Hello? Hello? Yeah, good morning. So, uh, I am starting with the chromatographic techniques. So, uh, have you do you have any idea about the chromatographic techniques, how it works? Yeah, exactly. So in the chromatography technique, basically what happens, it is a method to separate components in a liquid. Suppose we have a mixture of component A, B and C. So to separate those, we use chromatographic techniques. A basic, simplest chromatography technique is the paper chromatography technique, which you might have done in the experiments in the 12th standard also. So we separate the ink on the basis of their color. So that is a technique of chromatography, but there are different types again. So in the chromatography technique we have two components basically. First one is the mobile phase and the second one is the stationary phase. So the mobile phase, depending upon which is belongs to what. So generally in the chromatography we have a column and a solvent or our sample. So if the column is a stationary, so for example in this kind of morphology or this kind of technique, the column chromatography technique, in which the column is stationary and the material which we want to detect mobile is mobile phase. So that flows. So the like there are different types of chromatography again, but on the basis of the bed shape, basically we have column chromatography and planar. So planar one is the paper one which you might have used in your 12th standard. Then on the basis of the physical state of the mobile phase, we have gas chromatography and liquid chromatography. So in the gas chromatography, the sample is injected in a gaseous form, and in the liquid chromatography, the sample is injected in a liquid form. Then on the basis of the mechanism of separation, we have ion exchange chromatography, size exclusion chromatography, and expanded bed absorption chromatography. So I'm not going to detail with this. So I'll go towards the high performance liquid chromatography. So this is a very important technique and it is very widely used and it is very sophisticated. So here we have the column as a stationary phase in which we have a granular material with very small porous particles in a separation column. So this is the column which is having a granular material with very small porous particles, and the mobile phase is the solvent. So solvent is in the mobile phase, and then we inject the sample of in which we want to do the analysis. So depending upon the migration rate of the different elements of the in the sample, so we have a detector over here. So suppose the migration rate of A is faster than rate of B and C. So the element A or will come first, and the detector will detect it. So depending upon which their migration rate, the detector will detect, and we get the separation in our sample. So we know that how which what are the components which are present in our sample. So one by one they will get separated. So again, there are different types of HPLCs. So in the normal phase, we have a column packing in polar, that is, for example, silica, and the mobile phase is non-polar. So this is used for water-sensitive compounds, geometric isomers, and cis-trans isomers, and other compounds. Then we have reverse phase, in which the column packing is non-polar, and the mobile phase is water plus any miscible solvent, for example methanol, and or ethanol. So these are uh, mixed in a ratio of 50% or 80-20%, likewise, depending upon our requirement. And these can be used for polar, non-polar, ionizable, and ionic samples. Then we have ion exchange. So in this, so the mechanism behind is the exchange of ion, basically, because in the column packing we have ionic groups, and the mobile phase is a buffer. So it tries to separate the anions and cations, and that is how we separate these two materials. Then we have size exclusion. So again, depending upon their size, so the particles will diffuse on the basis of the pores. So so the column is a porous medium, right? So on the basis of their size, the particles will get elute. So the larger particles or molecules will elute first, and the smaller molecules will elute later. Then we have the gel formation chromatography technique. So this is a type of again a type of HPLC, and it is also called as size exclusion chromatography. And so again, as I told, on the basis of their size and hydrodynamic volume, the particles get separated. So it is used to determine the molecular weight distribution of the polymer. So here we have different terminologies, and the molecular weight is shown in this axis, and the elution volume or the retention time. Retention time is basically the time in which uh, the material will pass from the column. So this is the column. So when I inject the sample, so different elements will pass at different times. That is the migration rate. So the retention time, that means the time taken for the material to elute the column. So that is the retention time, which is shown here. And the graph is plotted likewise. And then the largest particle will fall in this region. Sorry. Oh, it's not visible. Oh, I'm so sorry. Okay, so yeah, actually, so this is the basic instrumentation of the HPLC. We have a solvent which is injected through a pump in the column, and the column is having a granular material. So it has small porous particles present in it, and we have an injector here. So with the help of the injector, we we inject the sample which we want to analyze. So and depending upon their migration rate, we detect it using a detector. So suppose the migration rate of A is higher than B and C, so then the first detector detects the sample A, that is the molecule A, then molecule B, and then molecule C, and then we get a data a plot like this. So like so that is what I was trying to say, that the elution volume is the retention time which a material is taking, a molecule is taking in to pass the column, basically. And the curve is obtained likewise in the gel formation chromatography. So this side we get the largest molecule, and this side we get the smallest molecule, and the separation happens in such a way that we get a Gaussian curve. So this is used to determine the molecular weight, and the determination is not absolute, but it is used for polymer standards with similar structure to correlate the elution time with the molecular weight. So the mechanism is that the size separation. So as you can see, the column is having a granules, and it has small pores in it, as you can see over here. So the size separation step occurs in the column filled with the porous particle. So this is the stationary phase and an entropic driven process. So this is a entropy driven process, basically. And the most common material used in these cells include the cross-linked polymers like polystyrene, acrylates, etc. So first the sample is dissolved in a solvent which is also used as a mobile phase, and the sample solution is injected into the column. Yes. Yeah. Yeah. Okay. So actually, it is not in a powder form. So if we have a sample in a powder form, we actually dissolve it in a solvent and then pass it through the column. So it has to be in a liquid or gas form. So films we can't do, but like the solution of the monomer before forming the film, that we can analyze using the this technique. Okay, or if you want to analyze after forming the film, then you have to dissolve it in some solvent, and then you have to do the testing, because the films we can't use in this, like in this technique we can't use the sample as a film because it has to be a mobile phase, so it has to flow. So normally we dissolve it in a solvent. So here, yeah. So again, here we dissolve the sample in a solvent, which is also in the the same solvent which we use in the mobile phase, as the mobile phase. Like as I showed here, the solvent here is the mobile phase. It try to elute the sample, like it try to make the sample flow from the column. So the sample is also dissolved in this particular solvent, and then it get injected into the column. So then after that the larger size particles will exclude from the pores, and in the that is in present in the stationary phase, that is the this granules, and the particles with a smaller size can enter them. So these granules are again having small pores, so the smaller particles will interact with these pores and it will not pass from the column, but the larger particles will pass from the column. So that is how the this separation works. So the theory behind it, we have a total volume of the column packed with solid matrix that has been swelled by water or other solvent. So the total bed volume will be given by the volume occupied by the solid matrix, then the volume occupied by the mobile phase, that is the void volume. So the volume in between the these granules, and then we have the volume of solvent which is held in the pores. So these small pores is also having some volume, so the solvent gets trapped in these pores, so that is the volume of the solvent. So for polymer separations, the pore sizes should be on the order of polymers being analyzed. So we have to check the, like we have to use the column in such a way that the pore size will should match with the polymer's molecule size. Then the theory behind it is that in the classical or in the classical science, the elution position of any molecule should be reported as the partition coefficient rather than its volume. So here we report generally the, like we calculate the partition coefficient also. So it is defined as the with this formula V minus V naught divided by Vt minus V naught. So V is the volume of effluent flowing through the column between the point of sample ejection and the sample emergence. So the starting of the column and the ending of the column. So this is the volume of effluent which is flowing. Then VO is the void volume, so that is the gaps present in the within the granules, and VI is the internal pore volume, that is the pores of of a single granule, that is the this volume, and the VT is the total volume of the like summation of internal pore volume and the void volume. So we have two voids over here. One is the voids in between these walls, and then the granule itself is having some pores. So this is the VI and this is the V naught. Okay, so this is the formula. So from here we can calculate the partition coefficient. So then again the GPC column is like this. It looks like these. So these are the columns. So these are put in together in series to form a bank, and it always put the highest pore size first, then from the injector, and the smallest pore size last. So this reduces the back pressure on the most fragile column. And so the ramp flow normally the speed is zero point 0.1 ml per minute or 1 ml per minute to 1 ml per minute, which is also done in very small increments. And the changeover solvent at a zero point 0.1 ml per minute flow rate is also done. So the uh, so normally we have different kinds of columns depending upon their sizes of the diameter and length. So the analytical column is having zero point 0.7 to 8 mm diameter. The predictive column we are having 22 to 25 mm, and then usual column length are around 25 to 30, 50 or 60 centimeters, and narrow bore columns are having diameter of around 2 to 3 mm diameter. So these are very very small columns. So once again, the instrumentation again. So we have the mobile phase, which is the solvent that has to be dissolved in the sample. So the sample must be dissolved in the solvent, and sometimes the polymer or insoluble are insoluble at room temperature. So we have to uh, heat them heat them at a high temperature to dissolve it. So, coming to your question again, so if you have a polymer film, so you have to, if it dissolves in room temperature, then well and good. But if it doesn't dissolve in room temperature, at room temperature, so you have to heat it a little bit to dissolve it in the solvent. So these are some of the examples like of solvents. Then the pump, so the pump takes the solvent and delivers it to the rest of the system, the column, and then pass it from the different instruments. So it makes it a constant flow all over, and it has to be accurate and reproducible flow rate. So that is how we need a very efficient pumps. Then ovens. So GPC is usually carried out at room temperature, but some instruments have heated and thermostatically controlled oven in which columns and detectors are placed. So operating the instrument at high temperature reduces viscosity, and hence the column back pressure will also be reduced and the system efficiency will be increased. Then some samples again, to prepare the sample for analysis, it is first dissolved in a solvent such as THF or other organic for organic GPC, and other solvents also like methanol or water also in some cases. The eluent used to prepare the sample should be the same as the solvent running through the sample. So the solvent has to be same as the mobile phase. The column packing are sometimes semi-rigid and sometimes rigid. So in the semi-rigid one, the cross-linked macromolecular polymers can be analyzed. These materials swell slightly. These are limited to maximum pressure of 300 psi. Bead diameters are usually 5 mm, and these are some of the examples like styrene dianyl benzene polymers, which are used for compounds of molecular weight ranging from 200 to 100 to 500 uh, million. And then sulfonated polystyrene beads are compatible with aqueous systems, and so in that cases we have to use a aqueous solvent, and also non-sulfonated with non-aqueous systems also they are used. So these are some of the examples of the beads which we use in the column. And other examples are dextrane gel, agarose gel, acrylamide gel. Then in the rigid one, we have a controlled pore size like glass or silica, and uh, it covers a wide range of pore diameter, which are also used for aqueous and polar organic solvents. So the detectors detect the concentration that is depending upon the response which we are getting, and we have a refractometer which uses this equation for the calculating the concentration, that is C. Then the structure selectivity is basically we have a UV detector or UV detector or IR detector. So depending upon the so the molecule has to be UV absorptive If it is not, then we are not able to detect. So the detector will not be able to detect unless it is having UV vis absorption or IR absorption. So this detector depends upon our application or our material. We select the detector. So normally the people use UV vis detector because most of the material absorbs UV or visible light. So that is the common one. But we also use the IR detectors sometimes. So then there are some formulas by which we calculate the concentration or viscometer, and again there are different detectors which, so using these responses, the using the viscosity or light scattering performance or the mass spectrometer are also connected with the chromatography, like the with the setup, and then depending upon those, the material is detected. So then we have a so this is a kind of detector which is detecting on the basis of the refractive index. So depending upon the like difference in their refractive index, the material will get uh, detected. So it has a light source and with a flow cell, and this light gets deflected if the refractive index is higher, and that is how we like depending upon their refractive index, the angle will be different, and then that can be detected on with using the detector. So so the light source shines the light into the flow cell. It contains two compartments, one of the pure mobile phase, that is the green one, and the other the effluent, which is flowing through the detector. So there is a refractive index difference between the two compartments, and the light will not go straight. So as we know the phenomena of reflection, the light will bend at an angle. So depending upon the refractive index of the material, the angle will be different. So this lead to the reflection of the light, and which is then detected on the with the help of a detector or the screen. So uh, that is how. So this formula of refractometer, using this formula we can get the concentration of the sample. Then the UV vis detection. So as I already told, that this is the most widely used. So if an analyte or molecule absorb light within the UV light range or visible range, this absorbance can be measured. It gives very high sensitivity and selectivity, and the gain information on the chemical composition, or also it can be used in gradient mode also, and excellent for these are excellent for polymer additives, and we can get a linear response because of the Beer-Emmert's law. So this law of absorption we use normally in the UV spectrometer also. So in the same with the same formula, we can detect the concentration, which is a linear response, and that's why it is a very sensitive technique for the detection of our chemical composition. And then the size excluded chromatography, we have it is usually referred as a DA by DC here. So this is the Beer-Lemmer's law, and so absorption is also in the SEC chromatography. We calculate the concentration with the help of this formula. The UV is absorption at multiple wavelengths or in combination of the refractive index detection allows it better determination of the composition informations. Then we have light scattering detector. So depending upon this light is getting scattered when it comes in contact with the polymer, and then it goes to at a certain angle to the detector. So after the scattering is happening, the detector detects the angle. So basically, it is based on a dynamic light, static or dynamic light scattering technique, which we also use for like normal characterization technique. But this is again a type of a detector which we use in the HPLC column. So that is how we get the column calibration. So mostly UVs gives a very linear this kind of response, and normally we plot the concentration with the retention time. So that is how we get the of the calibration curve of the material. So so these are some of the standards, and when then we can So we know the linear range of these standards at different concentrations, and the retention time is also known. So this is done using like we have to optimize first the material, and then with the unknown concentration, if it fits in somewhere in this line, we can know the concentration of that unknown sample. So that is how we generally do the perform the calibration. We have to have a calibration curve before analyzing any sample. So the sample preparation. So coming to that, to make a sample, we have to dissolve 10 mg of the dried polymer into 1 ml of inhibitor-free THF, and then it is injected. So these are the tubes which are used for the HPLC or GPC chromatography technique. So these are the vials which are having very small 20 micrometer PTFE filter, and every sample that is run on the GPC must be filtered. So these are having the filters, and the seal with GPC vial cap, and the and place in the automated sample holder, and noting its numbered position. So then there will be a manual ejection is also possible, or we can automate it also depending upon the position of these vials. So then now coming to the gas chromatography. So earlier we were observing the liquid chromatography. Now in the gas chromatography technique, the component of the sample are dissolved in the solvent and vaporized in order to separate the analyte by distributing the sample between two phases, the stationary phase and the mobile phase. So the mobile phase is chemically inert gas that serves to carry the molecule to the analyte, and it so through the heated column. So here we use a heated column, and the stationary phase is either a solid absorbent, or we just termed it solid gas chromatography (GSC), or a liquid or inert support that is called as gas liquid chromatography. So depending upon the stationary phase, the solid as well as liquid chromatography techniques are there. So the first, the liquid sample, it has to vaporize. So it is heated and the solvent will get vaporized, and we have the molecules left. So in the column, it gets separated into different depending upon their migration rate again. And then we have a detector which converts the amount of each component into the electrical signal. So this goes to the PC, and then we get the data depending upon their detection time. So the instrumentation is likewise. The sample ejection unit is having a heat which heats the liquid sample and vaporizes. So this is the sample ejection technique. It is a column oven, so it separates the so it is heated and the column separates the compounds, and then it goes to the detector which detects the compounds, and then it gives the signal on the PC. So there are carrier gases which are used. So it has to be dry and free of oxygen and chemically inert. So normally we use helium, and nitrogen, argon are also used. Hydrogen are also used sometimes, depending upon our analysis. So the desired performance and detector can be used. So hydrogen and helium are commonly used in flame ionization, thermal conductivity, electron capture, etc. And mass spectroscopy detectors uses the nitrogen or argon. So depending upon the detector again, we have to select the carrier gas. So the mass spectrometer uses the nitrogen or argon, which are having better advantage than the hydrogen or helium due to their higher molecular weights to improve the pump efficiency. Then we have fuel gas, so they support the flame in flame ionization detector, and which is normally a hydrogen gas, and zero air. So we have to have a vacuum all over to remove the oxygen or air from the column. Then column oven. So thermostated oven controls the temperature of the column. So as we know that we have to heat the sample in order to evaporate the solvent. So that is why the column oven is used. So it has the oven is operated into two manner. It can be either isothermal programming or temperature programming. So in the isothermal programming, the temperature is kept constant, but in the temperature programming, we have to we can increase continuously or gradually, or decrease depending upon our requirement. So we have to select the whether we want to use the isothermal programming or a temperature programming, that is gradient programming. So again, there are different column types for GC, like the gas chromatography. The capillary one, which is having a length of around 10 to 100 meters, and the inner diameter is zero point 0.1 mm to 0.53 mm. Stationary phase film thickness is zero point 0.1 to 5 micrometer, and it is mostly applicable to all the GLCs. So the gas liquid chromatography. It has very high resolution. The analysis time is short and high detection limit as well. So this is a widely used column. So here we have a liquid phase and fused silica over it. So liquid. So that's why we call it as gas liquid chromatography. Then the packed one is having a length of zero point 0.5 to 20 meters, and the internal diameter is 2 to 4 mm. The packing material is solid here, and which is absorbent, molecular sieve, activated alumina, silica gel, which are solid, support the support coated with thin film of stationary phase, and these are used for gas solid chromatography. But this gives low resolution and is used for a small number of components. So this one, the GLC, is mostly used. The capillary column is widely used because of its high resolution and short analysis time and high detection limit. So as I already told you, the uh, difference between these GLC and GSC. So the sample components are separated by their different interaction with the stationary phase, depending upon the solid phase or the liquid phase. And so the liquid stationary phases mainly fall into two types: the polyethylene glycol (PEG) or PDMS. The PDMS is having varying percentage of dimethyl, diphenyl, or mid-polar functional groups, and this separates the therefore non-polar columns with dimethyl or no, low percentage of diphenyl also are good for separation of so these are good for separating non-polar analytes. However, like so those molecules capable of pi-pi interaction can be separated by unstationary phase also, which are containing phenyl groups. So these are capable of hydrogen bonding to form, for example, acids or alcohols, are best separated by the PEG one. So the PEG one is used for the acids and alcohols, and because they are forming the hydrogen bonding, so they are capable of hydrogen bonding to like it derives the better, so the separation will be better, and so that's why uh, it is used for separation of those kind of uh, molecules. Then the GSC is having the station phase in solid, and again silica and alumina are used. Also the molecular sieve also are used. Then we have a like depending on, so the column also again having the retention time, which is the retention factor. Yeah, hi Bhupati. So I started the lecture earlier. I think we are a little late. So I'll be giving a brief about the column spectrum, column chromatography. Like, do you have any idea about what is a chromatography technique and how it works? Okay, you have not. So, okay, I'll again go to the basics of the chromatography technique. So, chromatography technique is mostly used for the separation of the components between in a sample. So, we have a stationary phase and a mobile phase. So, the chromatography technique is on the basis of the size or shape or chemical property of the molecule, or also the charge of the molecule, it separates the sample. So we have a in the chromatography technique, you might have done the paper chromatography technique in your 12th standard, the ink separation one. That is a basic example of a chromatography. But we have a different sophisticated techniques also, like column chromatography, Then our chromatography, this is the paper chromatography technique. Then we have gas chromatography, liquid chromatography. Then on the basis of the mechanism of separation, we have ion exchange chromatography, size exclusion chromatography, and expanded bed absorption chromatography. So here, as I told you, we have a stationary phase and a mobile phase. So in the column chromatography, the stationary phase is the setup that is placed inside the tube. So here the tube is having like granules or particles which are present in this tube, in this column, sorry. And then we have the our sample that is in the mobile phase. So that is in the liquid phase. So mobile phase, that means it will flow down to the column. So the this granules are stationary. So the column is stationary, and the solvent and the sample are mobile. So that will be flowing from the column. Then on the basis of the state of the mobile phase, so it can be either in gas form or liquid form. Then, depending upon the mechanism, I told you the ion exchange or size exclusion. So, in the ion exchange, we separate on the basis of cation and anion. In the size exclusion, the larger particle will flow first, and then the small particle will flow. I will show you how why this is why it is like that. That the larger will flow faster and as compared to the smaller. And then we have the expanded bed absorption technique. So and the HPLC is very widely used technique. It is very important one also. It is because it is highly sensitive. So here we have a solvent and a pump, which this solvent is the mobile phase which we are talking, and the HPLC column is having the granular material which are stationary. So this is the stationary phase, and this is the solvent, that is the mobile phase. So we have an injector with which the we inject the material or sample which we want to separate. So suppose the sample is containing ABC components, and depending upon their migration rate into the column, we detect it with the help of a detector. So suppose the so this solvent is actually helping the sample to flow in the column, right? So depending upon their migration rate, we detect it. Suppose the sample A and the molecule A is having a better uh, higher migration rate, so it will come first and the detector will detect it and give us the signal. So this is also this is called as the retention time, to be like in the technical language, the time taken for a sample to pass from the column. So initial from the injection to uh, to the detector, the time taken is the retention time. So this is the retention time which we normally like we plot it. So this is again a technique of chromatography. This is a type of HPLC which is gel permeation chromatography. So depending upon the size of the particle, we get the this kind of curve, and the retention time is also is plotted in the x-axis, and the molecular weight is plotted in this direction. And the largest particle will come first and the smallest will lie in this region, and we get a Gaussian curve. So so I was talking about the separation depending upon the size. So this is a column which is having granules, and there are voids present in it, right? So the larger particles will flow from these voids, and the smaller particles will so these granules are again having small pores in it. So the small particles will go in these pores, and it will not come out quickly. So the larger particle will flow from the column, but the smaller particle will take time to pass because they interact with these pores, and that's why they retard their motion. So the pores will retard their motion, and like with the help of this flowing solvent, this again comes it has to pass from the column, but it takes time. So that is the basic mechanism behind it. So there are different like theory for this. So the basically the theory is that we have the total bed volume, which is the summation of the volume occupied with by the granules, then the volume occupied by the void, like which is these are the voids which are present in between the granules, and then we have the volume which is held by the solvent or the pores. So these pores are having some volume, that is again the internal volume, which we call. So this the total volume is the summation of the solid and the void, which are present in between the granules and the pores volume. So again, there we can calculate the partition coefficient, which are generally, which is a technical term for the uh, like for this analysis, but we do not require it much. But we can calculate the partition coefficient with the help of this formula. So again, this V is the effluent volume which is flowing from the column. V naught is the void volume, and Vi is the internal pore volume. So Vt here is the total volume, that is internal pore volume plus the void volume. So for the larger molecules, the partition coefficient is normally zero. That is, void volume is equals to the effluent volume. And for the volume molecules that can penetrate all the pores, so the partition coefficient is one for them, and the effluent volume is equal to the total volume. Okay, so there are different columns for GPC. So these are put in series to form a band, and so the like it has the first one with a higher pore size should be kept first, and then the smallest pore size one will be kept last, and the flow rate is around zero point 0.1 ml per minute or 1 ml per minute, and also the solvent flows from the rate of zero point 0.1 ml per minute. So different columns are having different geometries or sizes. So analytical columns are generally around 7.5 to 8 mm diameter. Preparative columns are from 22 to 25 mm. The usual column length is around 25 to 60 centimeters, and the nanobore columns, which are very very fine bore, which is having 2 to 3 mm diameters. So again, the mobile phase, that is the solvent which has to be dissolved. So the sample has to be dissolved in this solvent, which is also used as the mobile phase. And the polymers, which are insoluble at room temperature, they have to be heated to dissolve in the at high temperature for this particular solvent. So the solvent is depending upon our choice of material. So a material, if it is soluble in THF, for example, so that has to be, so the THF has to be taken as a mobile phase. Then we have a pump. So a pump has to deliver or it has to flow the solvent at a constant and accurate rate, and the rate has to be reproducible also. So very efficient pumps are used. Then ovens. So GPC is usually carried out at room temperature, but sometimes we have to use a heater. So the columns are kept in an oven that is thermostatically controlled. So this is also so sometimes ovens are also used. Then samples. So as I told you that we have to first dissolve it in an appropriate solvent, and that solvent is the same as the mobile phase solvent which we are using. And the column packings, so these are sometimes rigid or semi-rigid. So rigid one are having silica classes which are having controlled pore size, and these are used for aqueous and non-polar and polar organic solvents. And then we have semi-rigid, which uses cross-linked macromolecular polymers, which is having a pressure limited pressure is around 300 psi, and these are sometimes swell also slightly because these are polymer. So these different polymers can be used for this kind of column packing. Then we have the detectors. So depending upon what we want to detect, so depending upon the concentration, we have the response. With a refractometer, we can detect the material. Then we have structure selective, that means UV detector or IR. So mostly UV detector are used because most of the material absorbs UV light. So that is why these are commonly used. But we also use IR sometimes depending upon our application. Then the molecular weight sensitive. There are some detectors which are sensitive to the molecular weight. So those can be used for in those cases if you want to detect the molecular weight. So the first one is the refractometer. This is a differential refractive index detector. So we have a light source and the flow cell is here. So the light passes to the flow cell and it has two components. The green compartment is the pure mobile phase and the other one is having the effluent which is flowing to the detector. So the light is passing through it and depending upon the refractive index, the light will bend and then the detector will detect the deflection or the angle at which the light is falling. So depending upon the refractive index of the material, the angle will be different, and then that is how we are able to uh, separate the material or components. Yeah. So next we have the UV vis detector. So this is the most widely used because most of the molecules absorb UV or visible radiation, and this is a very highly sensitive and selective method, and it gives us a linear response using the Beer-Lambert's law. So the Beer-Lambert's law gives us the relation between the absorption and the concentration again. So this is very useful when we have to plot the calibration curve. So these are sometimes like this is a very widely used detectors. Then we have the light scattering detectors. So these are based on the dynamic or static light scattering technique. So when the light comes in contact with the sample, it scatters in different directions or the different angles. So depending upon the angle, we detect the like the detector detects the light, and that is how we plot the curves or the spectrum. So then the column calibration with polymer standard. So column calibration is done because if we want to detect an unknown sample, so we already have to have a calibration curve. Then only we can detect the we can detect the unknown concentration of the material. So uh, so depending upon the retention time, that is how a particular typical graph of a chromatography technique uh, is what we get. It is in terms of molecular weight or retention time. So depending upon the molecular weight, the retention time will be different for different molecules. And then so if we have a calibration curve already, we know the standards, and then we can depending upon the unknown retention time or molecular weight, we can actually predict how much will be the concentration. So that is how we can uh, these calibration curves are useful in the chromatography technique. So the sample preparation. So here we have a polymer which is so suppose 10 mg of dried polymer we are taking which is dissolved in THF. So 1 ml of THF. Uh, why we are using THF? Because it depends upon our material also, but mostly polymers are soluble in THF, so we use it. But we can also again depending upon our material, our choice of material, we can select the solvent. So this dissolved polymer is then kept in the GPC vial, which is having a 20 micrometer PTFE filter. So every sample has to be filtered before run, so that's why we use these filters. Then this seal with a GPC vial cap, and then it is placed in the automated sample holder, and it can also be manually operated. So then these samples are like the samples injected from these vials into the column. So now second type of chromatography beside the liquid is the gas chromatography. This is also widely used, and in this the sample are dissolved in the solvent and then vaporized. So we have a heater over here. So it heats the sample, and then it vaporizes the solvent, and each components are in a carrier gas. So the medium here is a carrier gas. That's why we call it as gas chromatography. So uh, then we have the column, so it separates the compounds and then it goes to the detector. So the detector detects the signal, and that is how we can get our data. So the mobile phase is a chemically inert gas, and it should be uh, it should not be carrying any oxygen or anything. So, uh, we will talk about the carrier gas again in later slides. So the stationary phase is sometimes either solid absorbent. In that case, we call it as gas solid chromatography, or it can also be a liquid on an inert support. So in that case, we call it as liquid chromatography (GLC). So these are again two types depending upon the stationary phase. So this is the normal instrumentation of the gas chromatography. We have a sample injection unit which is having a heater. So it heats the liquid sample and vaporizes, then it goes to the column which separates each compound, and then the detector detects the compounds and gives the output signal. So the carrier gas, which as I was talking, that it has to be a dry and free of oxygen, and that's why we use it inert gases sometimes. That is helium and nitrogen, argon, and oxygen, and hydrogen are also used sometimes, depending upon their performance, obviously, and our application, and also the detector which is being used. So if we are using a flame ionization detector or thermal conductivity detector or electron capture detector, in that case we use hydrogen and helium. And if we are using mass spectroscopy detector, then we use nitrogen or argon, which gives a better efficiency as compared to the hydrogen and helium. Then we have a fuel gas. So in the flame ionization detector, the fuel gas is used, which is a hydrogen, and zero air. So the air has to be purified very well. Uh, these are the purified air that plays the role of oxidant to support the combustion of flame in the detector. And before being led to the gas chromatography, the above three are intermixed in the desired proportion. So the carrier gas, fuel gas, and zero air has to be mixed in a desired proportion, and it then passes to the chromatography, the column. Then we have the column oven, and which is used to set the temperature in the column. So this can be operated into two manners: isothermal or the temperature programming. So isothermal programming is the temperature is held constant, and which is the middle point of the boiling range of the sample. And in the temperature programming, the column temperature is either increased continuously or in steps as the solution progresses. So, as I was talking about the column, so column can be either solid or liquid. So, the liquid is one which is called as a capillary column. So, capillary column is using a liquid phase, which is having so the typical length is around 10 to 100 meter, and the inner diameter is 0.1 mm to 0.53 mm. Then the stationary phase film thickness is zero point 0.1 to 5 micrometers, and it is applicable to GLC again because we have a liquid phase. So that is why gas liquid chromatography it is called, and it is having a very high resolution, and analysis time is also short as compared to the solid one. So this is widely used. In the solid one, we have a it is called a specked column. Here we have a molecular sieve or activated alumina or silica gel, and the solid supports the coated with thin film of stationary phase. So these are having low resolution and are used for a small number of components. So that's why the liquid one is since it is having high resolution, it is widely used. So then again, as I told you, different phases are there. For the liquid stationary phases, the PEG or PDMS are used, and for gas stationary phase. In the gas solid chromatography, the stationary phase is solid, which is using a silica or alumina with porous molecular sieves. Then there are different terminologies for the column. So one is the retention factor. So retention factor is the migration rate of compounds in column. The migration rate of compound depends upon the compound chemical structure, stationary phase chemical structure, and the column temperature also. So the retention factor, which is given by this formula, Tr minus Tm by Tm. So Tm is the retention time of an unretained compound, equivalent to the time of the compound and spent in the mobile phase, and Tr is the retention time, which is the time spent by the compound inside the column. So if the interaction is stronger, then the retention time will be higher. If the interaction is weaker, then the retention time is less. So that is how we can calculate the retention factor also using this formula. So here the retention time can be known from the peak which we get, like from the spectra which we get from the from the detector. Then we have distribution constant. So this is the ratio of analyte concentration in the stationary phase to the mobile phase. And then the separation factor is also there, which is the measure of the time or distance between the a measure of the time and the uh, or the distance between the maxima of two peaks. So it is the distance between the two maxima of the two peaks basically. So alpha is 1 means the two peaks have the same retention time. Okay. So then we have the resolution. These are the formula for like calculating the resolution. And the baseline resolution occurs at r equals to 1.5 normally. So TR1, so suppose we have two peaks, so it has different retention time, TR1 and TR2. So and the peak width is also considered, peak width at half height. So the full width half maxima, that is the thing, which is denoted as WH here for two peaks, so peak 1 and peak 2. And the resolution is calculated using this formula. So then there are again for column efficiency, the number of theoretical plates, etc. that we can calculate using the same formula, these formulas. Then the height equivalent of a theoretical plate, S is equals to L by N. L is the column length and the N is the theoretical plate number. So this is a plate number which can be calculated using this formula, and then we can get the height equivalent. So there are different detection systems, as I explained earlier. So we have mass spectrometer detector. It has a detection limit of 0.25 to 100 picogram, which is the most sensitive one. Then we have flame ionization detector. Its detection is limit is 1 picogram per second. So these are used for hydrocarbons. Then thermal conductivity detector. These are universal, and this has a detection limit of 500 picogram per ml. Then electron capture detector. It is having a detection limit of 5 femtogram per second. And atomic. So these are used for hallucinated hydrocarbons. Then atomic emission. These are element selective, and the detection limit is 1 picogram. Then chemiluminescence. The oxidizing. It is used for oxidizing reagent, and the detection limit depends upon the dark current of PMT. Then photoionization, it is used for vapor and gaseous compounds. The detection limit is around 0.002 to 0.02 microgram per liter. So the most widely used is gas chromatography. This is so mass spectrometer is normally uh, is a spectrometry technique individually also, but it is also coupled with uh, liquid chromatography or gas chromatography, and it gives a better sensitivity. So it measures the mass to charge ratio of charged particles, and therefore can be used to determine the molecular weight and elemental composition, as well as elucidating the chemical structure of molecules. So data from the GCMS is three-dimensional and provides mass spectra that can be used to identify unknown compounds, plus the chromatogram that can be used for qualitative and quantitative analysis. So how does a GCMS instrument work? So a sample is a sample mixture is separated by the GC and transported by the carrier gas. Then the neutral molecule elute through a heated transfer line into the mass spectrometer. Then the neutral molecule are ionized, and most by electron ionization. Then in electron ionization, electron produced and accelerated with 70 electron volts and knocks at electron out of the molecule to produce a molecular ion. Then this excess energy of unstable molecular ion lost through various fragmentation, and then separate the ions of different masses, then based on their mass to charge ratio by the mass analyzer. Then this reaches to the ion detector, where the signal is amplified by an electron multiplier for most low resolution images, and a multi-channel plate for most high resolution images instruments. So that is how the GCMS instrument works. there are different mass analyzers: quadruple type, ion trap, magnetic sector, time of flight, and electrostatic sector. These are some of the like different uh, techniques for mass analyzer. So we have time of flight mass analyzer. So I'm not going to do because I'm running out of time. Then GCMS again. This is the kind of spectra you will get. The response with respect to retention time is what we are getting. So the two-dimensional chromatogram is produced by summing the abundance of all the ions at a single data point and plotting it against the retention time or scan number per scan number to produce a total ion chromatograph. And however, each data point in the total ion chromatogram is a separate mass spectrum. So as you can see here, the different data point are different separate mass spectrum altogether in this after the like processing. And then so this can usually be opened in a separate window in the software because it is giving it will so this is what we get from the GC, and in the MS we get peaks like this. So uh, these are opened in a separate file because it can be confusing sometimes. Then this is a example of a methanol. So here we have a base peak and then molecular ion peaks. So there are fragments of the single molecule also, and the most abundant peak is the tallest one and the most stable fragment also. So this occurs in a this signal comes in a fragmented manner because we are ionizing the molecules, right? So the fragmentation occurs like this, and then we get different peaks of that. So then we have the uh, BPA characterization. For that, we have to talk about the conductor, dielectric, and insulator materials. So conductor are the material which are electrically conductive, and it allows the charge to flow and ions to flow or electrons to flow from like one atom to another. So when a voltage is applied, so that is called a conductor. Then a material uh, which allows to flow of electric current with after a particular applied electric field is called as a dielectric. And these are dielectrics are non-conducting substances. They are the insulating material and are bad conductors of electric current. And dielectric materials can hold an electrostatic charge while dissipating minimal energy in the form of heat. So, and then we have the insulator which do not allow the flow of electric current upon applying an electric field. So, dielectric materials are important sometimes, depending upon our application, obviously. And these are insulating materials and are very poor conductor of electric current. But when dielectrics are placed in an electric field, particularly no current flows in them because unlike metals, they have no loosely bound or free electrons that may drift through the material. So instead, electric polarization will occur. So uh, there are different types of polarization: electronic polarization, dipolar orientation, ionic polarization, and interfacial polarization. So electric polarization is one in which the displacement of electron clouds is happening upon application of the electric field. So the electron field will displace from the nucleus, and that is how we get a distorted or electronic polymerization. Then we have dipole orientation. So when applying a electric field, the molecules will align. So these are the polar molecules which align with respect to the electric field, and that is what we call as electric dipolar or orientation polymerization. Then we have ionic atom polymerization. In this, the atomic polarization arises because there is a relative change in the mean position of the atomic nuclei within the molecule, and this generally small effect is observed at radio frequencies. Then we have interfacial polymerization. So this is due to the charge accumulation at the interface of two materials. So when a field is applied, the at the interface, the charge accumulation will occur. This is because of the difference in the permittivity and conductivity of two materials. So this is the interfacial polarization. So the dielectric response of the materials constituted at broad band frequencies and frequency maps of polymer and dynamics of polymer dynamics. Sorry. So we have electronic polarization which occur at this frequency, then ionic, then orientational, and then interfacial and space charge. So at higher frequency we get the ionic electronic one, and then at lower frequency we get the interfacial or space charge polarization. So now coming to the DETA, that is dielectric thermal analysis. So DETA, or it is also called as DEA, is a material science technique. It's similar to DMA, except for that an oscillating electric field is applied instead of a mechanical force. So we are applying here the electric field like instead of a mechanical force in a DMA. So it is a typical test where a sample is placed in contact with two electrodes, as you can see here, which act as a sensor, and so this and the sinusoidal voltage, that is electric field, is applied to one of the electrode, and then the resulting so this is without the external electric field, and when the electric field is applied, the polarization happens. So the negative and positive charges will separate out, and then the electricity will flow. So that is how then the signal is get to the response signal is attenuated in amplitude and shifted in the phase. So there is a phase shift because of this polarization. So this is the applied one, and this is what we get when we after the uh, uh, after there is a sample in between. So the phase shift is generally calculated, and that is what is used to detect the like what is the sample which is present in our material. So these are skipping for now. So this is a typical plot which we get, and this is between the tan delta and the log modulus, and so theoretically we should get a sinus wave like this, but experimentally it is somewhat like this curve we will get. So the uses and advantages over the thermal technique of advantages of DET obviously, and so these are mainly used to analyze polar samples. Materials ranging from thin film sheets, foams, powders, and liquids can be analyzed. Polymer properties examined by DETA are permittivity, measure of the degree of alignment of the molecular dipoles to the electric field, and the loss factor, which represent the energy required for the reorientation of the dipoles and ions. So the dissipation factor and conductivity are also examined. So with DETA, the electric constant and polarizability of the polymers are easily detected during the TG, that is the gas transition temperature, TM, melting temperature, and the PC. The application of the DETA is very similar to that the DM and DSC. However, it has various advantages over them. The data gathered from DETA are not affected by curing reaction, breakdown of additives, and blowing agent and degradation reaction, etc. And DMA is limited to 100 Hz, but DETA can go up to several Hz. So you can see the difference advantages of the DETA. So in the telecom application, low permittivity and low loss material are used. For that, we can perform the DTA experiment. Capacitors, high permittivity, radio frequency or microwave heating, high loss factors are there. A high loss is not a desired quality for a capacitor. Therefore, an ideal dielectric should have a high permittivity and low power factor. Power factor is the fraction of the electrical energy stored by the condenser in each cycle, which is lost as heat. So there are different equations. So for thermal decomposition kinetics of polymers, we have two major categories to study the thermal decomposition kinetics of polymers. So which are differential method and integral method. So the differential method contains Kissinger, Carroll, Freeman, and Friedman method, uh, while the integral method is having techniques like methods like Coates, Redfern, Doyle, Flinwall, Ozawa, FW method belongs to the integral method. So FW, Coates, Redfern, and Doyle methods are usually used for investigating thermal decomposition kinetics of polymers. So in general, the thermal decomposition of a solid polymer under inert atmosphere can be summarized as uh, suppose we have three elements. So B solid, and which gives solid plus gas. So polymer is finally decomposed into solid residue, that is C, and the gaseous residue, gaseous matter, that is D. So and B is the polymer, which is our sample. So the kinetic analysis of the solid state sample is usually given by this equation. So here we have R equals to, that is the kinetic analysis. Uh, this gives us, so this R is equals to d alpha by dt, that is the rate of conversion, which is equals to kT f of alpha. So kT is the temperature dependent rates constant. So there are, so depending upon the methods, there are different methods and uh, equations and activation energies associated with these equations. So first one is the Friedman, which is having this equation, and this is a very long equation. Um, so I'm not going to read it out, but these are the equations. So Friedman, and then FW, DAEN, and Kessinger equation. So disadvantages of integral and differences and disadvantages. So in the integral one, it is easy to use. It is used for simple rate expressions, can be used for scattered data, and only applicable for particular form of equation. But differential one, these are complicated to use and used for complicated rate expressions, used only for accurate data, and it can be used to develop the rate equation or to fit the data also. And the problem of integral method is the fact that Arrhenius integral function does not have an exact analytical solution. So thus several approximated equations have been proposed in literature, but normally like the differential one is the gives us the better accurate data. Now coming to the reverse engineering. So reverse engineering is a technique which is used in the rubber industry to perform chemical analysis and formula reconstruction of any rubber compound or polymers which is originated from different sources. So in the importance of reverse engineering is that we can get the analysis as a part of a quality assurance program to identify mixing and compounding errors. Then this technique is used to determine the composition of a competitor's rubber product, which is available already in the market, and the reconstruction of formulation of a compound by a particular product. So we can reconstruct the product by this reverse engineering technique. So suppose in the rubber product we have different ingredients which are elastomer, filler, protective agents, and vulcanizing chemicals. Elastomers, the properties will be different, users will be different, vulcanization can also be done. Then fillers, we have black fillers, non-black fillers, and vulcanizing chemicals, cross-linking agents, accelerators, activators, retarders, processing aids. Then the principal chemical and analytical methods which are used are chemical methods like chemical analysis, then IR spectroscopy, DSC, thermal analysis, DSC, TGA, DMA, chromatography technique, thin liquid chromatography, GC, HPLC, then atomic absorption spectroscopy, that is AAS, and microscopy and image analysis also can be done, and mass spectroscopy, that is also very important. Then physical tests like viscoelastic behavior, tensile stress strength test, then heat aging, set hardness, abrasion. This kind of analysis can also be done for the reverse engineering purpose. So the reverse engineering concept, we have a general concept and the formula reconstruction. So in the general concept, the first one is, first we extract the solvent, then ash content is determined, and chemical digestion and various instrumentation techniques are used later on. In the formula reconstruction, we have a sample preparation. We have to have a sample preparation, then brief description and use of analytical technique, and then the comparison of the reconstructed formula with the actual recipe. So the purpose of the chemical analysis is to analyze and comparison of the with the standard product. Then the analysis of deteriorated or faulty products or to determine the cause of failure. So that is in the that case also the reverse engineering helps. So depending upon the oxidation, like or thermal degradation or hydrolysis or swelling. What uh, what is the mechanism of failure? Depending upon that, we can improve our product. So that is also important. Then different analysis of the factor or errors which can be investigated, and the specifications has to be complied, because depending upon the buyers or government agencies, uh, their laws. So depending upon that, we have to compile those laws to verify our product on that basis. So in that case also we can this reverse engineering is important. So this gives us the broad knowledge of it in the industry, that is compounding practices, manufacturing methods, and analytical techniques, and can help a chemist in reconstructing a rubber compound formulation. So the rubber compound product is having physical properties, compound composition, and layout, and mold damage. So physical properties are tensile, tear, modulus, and elongation and break, abrasion resistance, hardness, ozone resistance, storage modulus, loss modulus, etc. Then composition, so polymer percent, carbon black percent, volatile metal percent, ash percent, total sulfur, and then types of volatiles, types of antioxidants, etc. can be determined. So the preparation of samples. So first we have to prepare a test piece for copper dimension to be tested prior to each test, and that the direct mold can be made from the mixed compound, and the specimens need to be cut, sliced, or buffed from the finished product. Then, so this is a total composition analysis of a tire cross section. So it has a thread, tread sidewall, inner ply, bead filler, inner filler, bead insulation. This is a case study. So to roll mill, first the camphor is crushed. Then the sulfur analysis was done. Sulfur analyzer, using the sulfur analyzer we can detect the total. We can determine the total quantity of sulfur. Then the composition analysis using the TGA or DTA curves, the percentage of polymer, carbon black, volatile percent, ash percent. Then the extraction using the soft slide extractor, solvent was extracted, and also sample can be extracted using chemical digester, or amount of carbon black is also then extracted. From the solvent extractor, we have chloroform fraction or the hexane fraction. The from the chloroform fraction, we can analyze it with using thin liquid chromatography. Then we can get the types of antioxidants which are present. Then from the hexane fraction, we can again pass it to the column chromatography. Then we have hexane part, a toluene part, acetone part, and methanol part. These are again analyzed using the FTIR to get the types of volatiles. Then we can analyze ash again after, like, um, this also can be done to observe the decomposed product. So these are different techniques which are used for physical property analysis, like tensile specimen, tear specimen, that is can be done using the universal testing machine. So here we can get the idea about the tensile strength, tear, modulus, and elongation at break. Then abrasion specimen, which is analyzed using green abrader, which gives us the abrasion resistance of the material. Then hardness specimen, that can be tested using the IRHD tester. It gives us the hardness of the material. Then DMS specimen, which will give us the dynamic viscosity elastomer, or the delta function of the tan delta value of the material. Then extraction. So this is a procedure for removing the organic additives from the polymer or carbon black or inorganic compound without simultaneously removing the significant amount of polymeric phase, while solution and dissolution involve the removal of polymer from the remaining composition compound. So extraction is different from dissolution, because in the dissolution one it removes the polymer also, but in the extraction it only removes the organic additives of the material from the material. So which material extract by extraction? In general, those extracted organic materials are of lower molar mass, but also include our polymeric plasticizer, factories, and mineral rubber. More realistically considered as plasticizers than polymers. So these are normally classifiers which can be extracted from with the help of the extraction process. Then choice of solvent. So again, for polymer, it should be slowed slightly by the solvent, but not should be soluble in it. So solvent which should be boiled below any extracted material so that it can be removed easily from the extract without loss of any extracted liquid and or heat damage to the solids of the polymer. Then solvent should be inert to any possible ingredient of this extract, non-objectionable by virtue of its excessive toxicity, inflammability, or odor, and it should be cheap so that it can be reused or recovered solvent should be avoided. Then, so different elastomers will be having different uh, compounds and vulcanized. So methanol is generally used for useful solvent for the qualitative extraction of the natural rubber and raw or vulcanized rubber for subsequent chromatographic examination of the extract. So these are some of the um, solvents which are generally used for the extraction of different types of elastomers. Then the resistance of rubber to various solvents. From this table, you can get an idea about what if you are materially suppose getting dissolved in ketones or alcohols, then you can get an idea about like which what is the possibility of the uh, probability of the sample to be this in this from these types. Which one is the best fit? So with the help of the resistance to rubber and the solvent, we can get the idea about this our material. Then, so as the extracts, so then the extracts are then uh, analyzed using the so different uh, techniques are there for the analysis of extract. And then there are various plasticizers which are present in this rubber, so natural rubber or SBR or again different materials are in different plasticizers. So various grades of mineral or hydrocarbon oil are present as a plasticizer in these rubbers, and oxygenated compounds or esters are present in PVC, PU, and MBR. So with the help of the extracts of the plasticizer, we can get an idea about in which domain the our material falls, whether it is PVC, PU, or NBR, or it is natural rubber or SBR or something like that. Then the properties are also different for the different plasticizers. So for phosphate-based plasticizers, the density are different, the refractive index are also varying in the same, and the boiling point is also different. Then phthalates again, so these are for phosphates. Then we have phthalates, and so then again different mobile phases are used for separating antioxidants on silica gel. So silica gel is normally used in the solid chromatography technique. So and then we have a mobile phase which is using a solvent. So to separate the antioxidants, we have to dissolve the material in the mobile phase, or we have to use the same solvent which we have used for the antioxidant. Uh, in the mobile phase also, we have to use the same solvent. So generally we use these solvents, that is benzene, hexane, chloroform, cyclohexane, benzene, acetone, toluene, and these are some of the solvents which we use to separate the antioxidants. Then again, in a particular ratio, we can use it like select it depending upon our material. So this is the basic flow chart. So we have a rubber compound. We extract it with in terms of additives. These additives are characterized with using the TLC, HPLC, GPC, IR, UV, MS, NMR, etc. Then the insoluble part are extracted again. And polymer, if it is a polymer, we characterize it with IR or NMR, and the fillers are characterized by AS, EDX, TM, IR, etc. So this gives us the opportunities for direct analysis. So from the analysis plan, it is clear that methods which permit the simultaneous analysis of the polymer reduce and fillers in a single operation not only saves time but reduces the cost of analysis also and raise productivity. The use of new analytical techniques like FTIR, then TGA, pyrolysis mass spectroscopy, and in the analysis of vulcanized has made a goal to the direct analysis, and uh, like it can be achieved towards by using these sophisticated techniques. Then we can select the NMR technique for the detection of the polymers sample and without decomposing the sample. So that is again a good technique. Without decomposing the elastomer, we are able to detect the sample. Then we have the using this technique, the direct detection of monosulfadic or polysulfadic and carbon-carbon cross-linking sites also can be achieved. So then, then we have the NMR, UV, or IR spectroscopy, which are not normally possible until the constituents of the extracts have been separated. So in that case, the direct qualitative analysis of the extract is possible, but again we have to have some kind of extracts uh, from the polymer. So then we have GC and GPC and liquid chromatography technique to get a good separation of the extracts and its constituents in polymers or elastomers. Then with all these separation methods, extract constituents can be identified by comparing the measured retention parameters with those of the known substance. Then GC is particularly suitable for characterizing and quantifying constituents of relatively high volatility antioxidants and oils. And by comparing the GC with FTIR spectroscopy or mass spectroscopy, one can also determine unknown ingredients which are present in the extract compound. Then we have thin layer chromatography. So thin layer chromatography is an inexperienced and easy way to determine unknown rubber processing ingredients for formula reconstruction and quality control. So TLC is having advantages over HPLC, IR, and UV. HPLC is a useful technique for identifying rubber compound ingredients, but it requires a longer time for analysis than the TLC. So TLC is better in terms of cost also. SPLC is expensive and immobile, but TLC can be is cheaper in that way and can be used at different places. Then silica gel absorbent is the traditional absorbent used for TLC, and since the solid phase is more polar than the mobile phase, when silica gel absorbent is used, then it gives terms as normal phase chromatography. And in the reverse phase chromatography, involves the use of a non-polar material, which is usually the hydrocarbons, which is in the stationary phase, and the polar is the solvent, that is the mobile phase. Then, so the mobility is measured in the with this formula RL, that is the different distance traveled by the compound divided by the distance traveled by the solvent frame. So this is the formula for the determination of mobility in the thin layer chromatography technique. So the extracts can be analyzed with the TLC, as I have told you the advantages of this, and it is particularly useful for the to analyze the not only polymers of competing products but also their low molecular accompanying substances also. So it is relatively easy to determine antioxidants and assertion with what type of processes are present. It is often impossible to reconstruct the vulcanization system from the acceptable fragments and reaction products of accelerators. The low molecular accompanying substances can be analyzed using the IR in junction with the TLC, and it is mostly a standard technique for this. So IR is the standard one, and TLC is also can be done. Then phenolic and aminic stabilizers are likewise often recognizable in the IR spectrum, which is in the range in the of 3600 to 3300 centigrade inverse. TLC analysis of the antioxidants is also sublimated in that way. So the different plasticizer types are having different IR bands, as can be seen here. And the organic fillers and trace metal analysis are ashing again is the one of the process. So this ash determination of this pyrolite samples can be done, and with that we can from the continuous oxidative heating we can get the ashes component, and that can be again again characterized to get the idea about the trace metal analysis, metal fillers analysis can be done. So then the mineral constituents also can be observed after the uh, ashing process. So depending upon different standards, we have to use the different ISO standards for these characterization. And also there is a dissociation pressure associated with the different materials and at different temperature rate. So we have to have take care of this. So normally there is a whitish ash which is also because of the calcium carbonate formed upon decomposition with the heating using the because of the interaction with the carbon dioxide while heating. So the dissociation pressure of the CaCO3 are as follows with different temperatures. So then we can again detect the trace metals using the AS, that is atomic absorption spectrophotometry, which is used to determine a very trace amount of metals present in a material, which is up to less than 1 ppm concentration. So then there are physical analysis can be done. As I already told you, there are different standards, ASTM standards and instruments which has to be used, like for the analysis of a tire compound. So tensile strength, modulus, elongation rate can be used for um, can be determined using the UTM technique. Then tear strength can be again checked with the UTM. Then abrasion with the denabrator, hardness with the IRHT, ozone resistance with the ozone chamber, then DMA with the DMA instrument. So then metallic compounds in the filler can also be processed, and from the thermoanalysis detection we can get the idea about at what temperature the different components of the material are getting degraded. So first there will be a glass transition temperature, then with some of the ingredient will heat at some temperature, then water loss will be occurring, then crystallinity melt will occur, which is for oil basicizers and vulcanization. Then vulcanization will happen, and then oxidation either or degradation will happen in a particular elastomer sample. So we first do the DTA, then DSC or differential scanning or derivative differential scanning (DDSC). Then thermogravimetric analysis was done, can be done. Then thermomechanical analysis (TMA) and DMA, dynamic mechanical analysis, can also be performed. So with the DSC, we observe from around -100 to 25 temperature range. We observe the glass transition or crystallization. Then from 25 to 150 degrees centigrade, we observe the melting additives. Then from 150 to 220 curatives, vulcanization event will be observed, and about 220 thermal degradation or oxidative degradation will be occurred. So the application is that it gives us the idea about the glass transition temperature and the melting temperature of the material, and also the crystallization will also be uh, uh, that can be detected. And the polymer having a lower Tg than room temperature and amorphous nature behaves as rubber, and Tg of fiber and plastics is above room temperature. So, yeah, depending upon the property of the material, the Tg will be higher or either lower. So, the higher value means the higher will be the flexibility of the rubber. So, these are some of the typical polymers which are present or normally used, which are having Tgs in the range, and the melting temperature is also mentioned in some of these. So the factors which are increasing the Tg, that is the glass transition temperature, are the main chain rigidity, the increased polarity, or bulk or rigid chain chain, or the increased molecular weight or cross-linking. And the factors which decrease the Tg are the main chain flexibility, addition of diluents, addition of plasticizers, and the branching. So then the definitions in the TGA of like how of the TGA and most of the elastomers. that we get the highly volatile metal, which is the normally solvent or moisture or oil which is present in the material. Then medium volatile matter, which is the major elastomer rain or the curing agent or processing aid, which are used in this region. Then combustible material, which are oxidizable material but non-volatile and uh, which is in the unoxidized state, and some stipulated temperature dependent of the material, that is carbon black or graphite, etc. Then we get the ash, which is not degraded at all, but it is oxidized non-volatile residue in the oxidizing atmosphere. So these include the metallic oxides, fillers, or inert reinforcing material, which are still present in the material above a certain temperature, but it is not getting degraded. But it will be in the form of a ash, and it is majorly the oxidized metals and the fillers. So the amount of carbon black can be calculated using the DTG method, and the ash uh, percentage can also be calculated, and the oil oxidizer can also be calculated using the formula mentioned here. So here, as I told, the first one is the oil or ash. Then we have the polymer degradation. Then the carbon black will degrade, and then the remaining one is the ash, which is not getting degraded, but it will remain as the oxidized form. So yeah, so different materials are having different temperature of degradation. So initial, medium, and final degradation temperatures are mentioned over here in presence of a particular atmosphere like nitrogen or oxygen gas, or the composition or the mixture of both. Likewise, the TZ experiment can be done. So reverse engineering provides the quality assurance guidance for both manufacturers and purchasers of rubber goods. This includes the quality assurance of raw materials and evaluation of different processing parameters during mixing and vulcanization. And finally, the vulcanized product must be stable in the end-use environment, which may include a wide range of temperature, high or low, contact with chemicals or solvents, and oxidizing and reducing atmospheres. And the product must contact its chemical composition and physical properties under these conditions during its expected service life. And the thermal analysis can be valuable a tool for all these stages, from quality assurance of raw materials to processing and vulcanization and analysis of the vulcanizer and its environmental stability. So that we need to keep in mind. So now coming to the questions. So in what order will the following substance elute in HPLC column tagged with C1s hydrocarbon bounded to the siloxane backbone? So we have a siloxane backbone which is bonded with a hydrocarbon. So which among these will what should be the order? So first, which one will flow? Acetone, acetamide, or 1,2-dichloroethane? So can anyone of you guess what should be the answer for this? So here we have a C1s hydrocarbon bomb. So the material should be uh, reacting to the C1s. So the material which is mostly reacted with this hydrocarbon chain will elute last. So the this dichloroethane, which is having a hydrocarbon chain, so it will try to bind with this hydrocarbon. So that's why it will elute last. So the option is this A, that is this will elute last. Then acetone will again is having some kind of hydrocarbon, so that will elute at the second position, and the acetamide will be the first one to elute. So that means it will not bond with the hydrocarbon. So that is how the uh, basic mechanism that it works in the HPLC, and this is the order in if for this for these materials. Then the second one is the a patient drunk sugar, salt, alcohol, and vitamin C simultaneously. A gas chromatogram could be used to determine the only alcohol content of drink, or both alcohol and salt content, or sugar, alcohol, and vitamin C content, or only alcohol and vitamin C content? Can any one of you can guess what should be the answer for this? Okay, so here we have sugar, salt, alcohol, and vitamin C. So in the salt, the it will get dissociated into ions. So that will not be. So in the gas chromatogram, it won't be able to detect because the ions can't be detected with this. So we will be able to detect the sugar, alcohol, and vitamin C content of the drink. So that is the correct answer. Okay. So C is the correct answer for this because salt will ionize, so that won't be able. It has and it has small particles also, so that won't be able to be detected in the gas chromatograph. Now, the interaction between the polar and non-polar molecules are termed as Keystone interaction, Debye interaction, London force, or none of the above. Any guesses for this one? Polar and non-polar molecules. Sorry. Mm, no, it should be Debye interaction. So the interaction between polar and non-polar molecule is the Debye interaction, not Keystone. Then the next question is the activation energy of thermally stimulated process in DSC, TG, and DTG are determined by which method? Friedman method, Kissinger method, both A and B, and none of the above. Yeah, both A and B are correct. So Friedman method and Kissinger method both are used for the determination of activation energy. Then the process of taking something apart from and analyzing its working in detail, usually with the intention of understanding its structure, function, and operation, termed as reverse engineering and product analysis, smart engineering, or none of the above. This is a simple question. I think you will be able to answer. Any guesses? Like A, right? So this is the reverse engineering which we just talked about. So it is basically the process of understanding the structure, function, and operation for the purpose of and then analyze for the purpose of understanding what is inside the sample or material. So that is the reverse engineering process. So with that, we are done with today's session, and with that, we are done with the 12-week course also. So uh, for those who are taking the exams, all the best to you, and all the best to all of you for your future ahead. And if you have any doubts, you can ask on the in the portal also. And thank you so much for joining.